Okay, I will just make it brief. So this is Carsten. Carsten is part of the part-time scientists who want to send a rover to a place where it's very hard to do 3D printing. So enjoy this talk labeled 3D printing on the moon, the future of space exploration. Stage is yours.
Hi. So who of you knows about the Google Lunar X Prize? Just, okay. What? Okay, it's okay. You don't have to know. I was just checking. Okay, so we're a team called the Part-Time Scientist, and we were founded like 2008, so that's quite a while ago, with 6 people. And as of today, we are about 35 people that are working on a mission to the moon. And of those 35 people, we have now 11 employees, which makes the name Part-Time Scientist a lie. So on the corner of the slide, you see our new logo. It's a PT Scientist. And yeah, well, we don't know what the PT stands for yet, but we will figure it out eventually. So, so for those of you that have seen our presentation last year, it was we did win the milestone prizes. So we won $750,000 for qualifying our rover, which is quite nice. And we also got a new partner, which is a bit significant. It's Audi, and yeah, we are cooperating with the DLR, with NASA Ames, and various other partners to get this mission done. But yeah, and the Google Lunar X Prize is a competition where you can get $30 million for sending a rover to the moon. So, and this is where this is our vision. We want to send a rover to the moon, and it should somehow look like this. This is actually what we are currently working on. So that was me yesterday. The lines main, everything is fine, which is why I had no time to prepare the presentation, so I hope it's okay still. Yeah, we're working very tirelessly on getting that done. The cool thing is that our new rover is actually a little bit bigger again. You know, we started with like a very small one, and we figured out that it's too small. And we increased it a bit, and it's too small again. And the last size increase came in the form of the wheels, because we found out that with more surface we can climb up higher slopes, and also decreasing the weight was very helpful. And the cool thing about the new rover is that the wheels that you see on the left-hand side is a new wheel, and it's 200 grams lighter despite being bigger. And we were able to do that because the left one is fully 3D printed. And this is pretty darn cool. So we are a big fan of 3D printing for everything we do, not just because we're always tight on time. So it's also very helpful that you can get 3D printed stuff quickly. We could be more organized, but well, we have 3D printers, which is much cooler. Except, so 3D printing is hard. You probably know, especially those that made the ones on your own. It's yeah, it's very tough to get it right, because the material that you get out of the 3D printer is not what you actually expect and what can be used. But we want to do it on the moon anyway. So yeah, this is just a nice picture that came up from NASA. No, was it NASA? It came up and it's looking very nice. So we want to take the picture of that, and we want to land near Apollo 17. So that's the Taurus Littrell Valley, which is near the equator, and it's we want to land like 5 kilometers near it, and there's in a 1 kilometer landing ellipse. So that's hopefully the landing area, not the impact area. We are working on that. One of the dates I suggested for sending a rover to the moon was to start on the 7th December in 2017, because that's like 45 years after Apollo 17 happened. And also we would land on Christmas, and so if someone asked what we would do on Christmas, it would be like, I could say, well, I made a new crater on the moon. So hopefully we don't do the crater thing. The reason why we chose Apollo 17 in this past is mostly because it has a very interesting geological property. It was the one mission where NASA say, oh, we don't do it just for show, we actually want to do science. And so they took a geologist with them. And so there is some known data about the geology of Apollo 17. And so that's one of the reasons we want to go there. The other reason is the lunar rover vehicle that you can see here. We want to do significant science when we go there. Now, we don't just want to win the Google Analytics Prize. We want to do real science there, and we want to. One of the science objectives, as it was said by NASA, is that they want to see how the stuff on the surface after 43 years of exposure is still there. You know, whether it was shot into little pieces, or you know, maybe they find some other reason why they didn't, why we didn't find anything there. But yeah, the lunar rover vehicle is made of all kinds of things like leather and piano wire, fiberglass, and it's interesting to see how that worked. So this is Apollo 17. Yeah. But now for the interesting part about 3D printing on the moon. So the surface material of the moon is made up of lunar regulus, which is made of silicon, aluminum, titanium, iron, oxygen, and kind of other stuff. And it's very, very fine powdered. So when you think about the moon, it doesn't have any atmosphere, so there is nothing that could, you know, transport the lunar dust around. So it's sitting there for years and years and millions of years. And there are always all those tiny micro meteorites which are bombarding the surface and smashing the surface into very, very, very fine powder. And this powder has some very interesting properties. So the question is, how could you actually use this material for doing 3D printing on the moon? And there are like 3 options. One we like very much. This is the microwave-based manufacturing. So the idea behind that is that you're using like an ordinary microwave, or the magnetron of it, and you melt up the material because it contains some iron, and then you can get a solid surface of that. The problem with that is the regular simulants, which are used for testing, for various testing of of testing rovers or spacesuits or anything alike, they are well, you can microwave them, but nothing happens, which is kind of bad for testing because this makes it very difficult. But there is one interesting property that is at least known for some of the Apollo 11 and Apollo 17 samples, and this is that it contains some iron. You can see those little iron. This is elemental iron that is enclosed in the glass, and this is very. This absorbs the microwave energy very efficiently, and so with very little energy, you can actually get a liquid phase between the particles, which then heats up even more, and there is a runaway thermal reaction going on so that you get a solid material after you bombarded it with microwave. And the question is, what can you do with that? I mean, the microwave is not as focused as, for example, as a laser, where with a laser, let me start a little earlier. So if you want to do laser sintering on the Earth, or actually anywhere, but if you want to do, you take aluminum powder, and you take a laser, and you melt it, and then you put on another layer of this aluminum powder, and then you melt it again. And with that process, you can actually 3D print aluminum. And if you want to do that on the moon, you can create very fine structures. But with the microwave, you are not so focused. And the question is, can you still do anything interesting with that? And the answer to that is yes. If you have a microwave, you can actually make a surface coating of the regolith. The problem that you have when, for example, the Apollo astronauts were coming back into their capsule, they had the problem that the regolith is so fine that it actually went through their spacesuits, and they got black fingers. And so the idea is when you're creating a surface coating by microwaving the surface, then you have a solid thing where you can drive on, where you don't generate as much dust when you're landing or when you're driving on it. And thus, if you want to build a lunar base and you have to go out often, then not dealing with as much regolith is a very nice property to have. Also, there's some interesting ideas that you can actually make a radio dish with that. So you take a regular crater and you surface coat, and you have an almost perfect antenna. Well, eventually, after a few decades of work. Yeah. So one of the ideas that was proposed is this boring lawnmower. But we think of something cool like this one. So the idea is that you have the magnetrons on the bottom side, and while you are driving, you're actually irradiating the surface, and this irradiation brings the surface, the material to about 1,200 degrees Celsius in a very quick time. And this starts the melting process so that you get the very nice coating. And because we're using microwave, this is very power efficient way of doing that. This is also why we are aiming to send a little experiment to the surface of the moon with the microwaving thing. Also, it's very interesting to do that because we are very power constrained in our payload opportunities that we have, and we are also we want to do something simple, and if you want to build a laser regolith printer, then stuff gets very messy. But I will show you some pictures later on. So, if you want to go into additive manufacturing, there is significantly more to building a 3D printer than just having the ability to melt the material. The problem with the regolith is that not all material is well suited. So you need to collect the material, you need to refine it in some way, and then you can use, for example, a laser to melt it. The other thing that, for example, ESA is thinking about, who of you knows actually the Moon Village idea of ESA? Okay, yeah, ESA is very popular. I find that people know more about NASA than they do about ESA, interestingly. So what they want to do is they want to print a 3D base. They want to 3D print a base, and they want to do it with a clue that they are taking with them, and so they want to use a binding material for the printing process. And we think that's maybe not the best idea. If you can do it just with energy, which you have plenty of because you're on the moon and there is no atmosphere, then that's significantly better than using a binding material. And yeah, so ESA is supporting the idea of using a binding material, but I think that the laser printing one is the one that we are using now, and which is probably the most mature, and so that's probably pretty good. But how do you actually separate the materials that you that you want to use for printing, and so not all of the material is printable or is ready for sintering, and so you want to collect material that is small, that is at best fine powdered, which you have plenty, but the coarse size, the size of the particles is very oddly shaped. So it's a little bit difficult to collect the material and to process it so that it can be used for laser 3D printing. And this is where this sucker comes in. It's a lunar soil magnetic collector, or lunar soil sucker, as it was called. And it's basically a railgun in reverse. So you take magnetic fields and you use the property that the regulus material, or the part that you're interested in, is actually magnetic. And so you're transporting the material in this sucker, and it's floating in some reservoir, and then you can do your whole 3D printing with the laser melting and putting layer top on layer. Yeah, that should work. It's, you know, when you're doing a mission to the moon, you know, for the first time in a few decades, and you're doing it as a private entity, and you started as part-time scientist, that's not the thing you want to do on the first try. So we're keeping the best for the next missions. So baby steps first, not make an impact crater, and then microwave the lunar soil. Actually, someone did use the lunar regulus simulants that are available and actually build such a 3D printer, which is easy if you're on Earth and you have the regulus printer and you're actually sitting by the printer, and you can, you know, do a Russian repair by knocking it when it's failing. And the results are, well, like this. I don't know if that is good or not, but it's something, and it was 3D printed.
Awesome.
Yeah. Well, I mean, you know, so the good thing is that in theory, the laser bell-based melting should actually work. The problem with laser-based melting is that a lot of the energy that you are, so if you're building a laser, a lot of energy that you put into it is not converted into optical energy, which goes out of the laser thingy, and then you point it at a material that is not black. It is, in this case, it's more likely gray, so you have some reflectance, and so a lot of energy is wasted in this way when you are using a laser. But as said, the advantage is that you can make very fine structures, or as fine as this one. I actually don't know if that's inch or centimeters. It's small, it's something. I would give it a C for effort. Yeah, I mean, if you know 3D printers, you know, especially the aluminum sintering things, it's very difficult to get right. With the problem with 3D printing is always the material feed, right? You have the material, you have the PLA, for example, and you put it through the nozzle, and in theory it should work. In practice, well, not often or not always. And this is the idea as presented by ESA. And as a company, we have to think about business cases, and the best we could come up with was, we are helping them do this, and this is the ESA vision of having a 3D printed multi-dome structure, or moon village, as they call it, and they are working on it. I don't know what the current state is, but they are planning to do it. And as said, they have those glue-based printers, and I think printing a 3D printing a base is a very good idea, because you want to use as much of the resources that are locally available as possible. Because bringing one, to give you some perspective, so we want to bring something on the moon, which is our rover, which is about 30 kilograms. Actually, we want to bring a bit more, but back to that later. So we start with 30 tons of rocket on Earth, and until we are getting into the orbit, we are down to 1.5 tons. And the 1.5 tons, they fly to the moon, and then they do the soft landing part thingy, and then we unload the rover, we collect the money from Google, make a party, and we get about tops about 100 kilograms of payload mass to the surface, starting from 30 tons on Earth. So the ratio is very bad, and so you want to use as much resources as possible, which is called in situ resource utilization, which is now a very active topic among planetary researchers because of the rocket equation and the ratio that I told you about. Another very fancy idea about how you could actually print something is to make a thermite reaction. So you take the material, split it into the right parts, and then you ignite it, and you should have a thermite reaction, which you can use for casting then. Well, apparently it was tested with some simulants, and it should work. Whether it really does, well, I don't know. But yeah.
What is a thermite reaction?
Thermite is the what is it? Iron and aluminum. Iron oxide and aluminum. Yeah. So you take iron oxide and aluminum and you ignite it, and then they start off a runaway reaction. And this is used for example, for gluing together the railways. So it's a very nice reaction. The temperature goes up very high, which makes it a little bit hard to handle. So not on the first try. Yeah, so I told you about those ideas. We are looking for people that do help us, for example. And so the question is, what are we next? What are we up next? And among the things that we are working on right now is our rover. We are very happy about it, if it works as we plan. And this next thing we start on with next year is to build actually the lander. And so if you're interested in building a cold gas flying thing like this, something like this, you're very invited to join us and to shoot us an email. And one of the things that I forgot to mention, we also have payload opportunities. So we are selling actually some of the payload that we can take to the moon. And if you're interested in helping us to shoot microwaves at some real lunar regulus, we're looking forward to hearing from you. And unfortunately, because I didn't have much time to prepare the presentation, and actually already done. But I hope you have tons of questions, and I hope I can answer them to you. Sorry. Thanks.
That was am I on? Yes. That was a quick and I found it very interesting talk. So if you need to leave now, please do so quietly. And if you have any questions, please line up at the microphones on the right or on the left side. And please keep the voices down so we can hear the questions from the microphones. So if you want to talk, then also leave. That would be very nice. So please be quiet right now. Quiet. Very quiet. Okay, very good. So first question on the right side, the front microphone.
Hello. So you mentioned a rocket of about 30 tons. Are you currently engaging with anyone that's building these rockets or selling them?
Yeah, we are in negotiations with the Indians regarding the PSLV XL. So we plan to use that one. We are also in discussions with other alternatives. Yes, so we are in discussions about that.
Okay, are there internet questions? There are at the moment no internet questions. So next question from, again, the right microphone.
Hello. Can't you simply melt the regolith by focusing sunlight?
Oh yeah, that was the third alternative that we were also thinking about. The problem with that is that you need to have so the target temperature that you're aiming for is about 1,200 degrees Celsius. If you want to use sunlight, you would need to collect enough to create about 40 watts of heat in a very small area. So you will need to have a rather large optical thing. And if you know optical things, those are fragile. And launching in a rocket is the exact opposite of of having a chip by DHL. Well, I don't know if that's. I don't know who I was insulting with that, DHL or the rockets, but anyway, so it's you can take the in theory it would be possible, yes, and it has been tested. The problem is that you need to have a mechanical constructions for focusing and for getting it to the moon. And after you have done that, you also want to do something useful with that. So you need to not just focus it on a point, but you need to move around the focus point as well. So from a mechanical construction point of view, that gets very difficult, which is why we especially like the idea about the microwaving, where you just create. It's not really 3D printing, but you're showing some interesting prospects about the regular surface, and that is not possible with the simulant. So this is why we are preferring that.
Okay, next question on the left side, the front microphone, that's you.
So I think there is currently also a challenge from NASA to do 3D printing of habitable modules on Mars.
Yeah.
Do you have some something to say about that? Like what the difference is to Moon and what methods might work?
I know about the challenge. I think it's a very good idea. I didn't investigate it too closely, I have to say, but I think that in some ways the lunar regulus is easier to handle because you have those elemental iron that is sitting in the class beads, and but maybe I'm wrong. So it's both very difficult to 3D print on the Moon and to 3D print on the Mars, but I cannot exactly tell you which one is more challenging. It's sorry, I don't know, but I could imagine that when you're thinking about 3D printing on the Mars, you're most probably not thinking about, or maybe you do. I was thinking about robotic missions. So when I'm thinking about Mars, there are always people there already, while on the Moon there's no one, which is stupid. But yeah.
Okay, a question from the internet.
Yeah, the first question is it possible to focus a microwave sharp enough to get laser quality precision in the 3D print?
That's a very good question. In theory, with some antenna designs, it should be possible, but it might be difficult. What do you say?
It depends on the wavelength.
So the expert answer is it depends on the wavelengths. Yeah, no, I would say that it's definitely more challenging than having a laser where you have the concurrent light anyway. So it would be probably a bit more difficult to focus it. But the interesting thing about, we know from with a laser that it works with the simulants, and so we can test it on Earth. But with a microwave, it doesn't work on the moon, on Earth. And so I think it's more interesting to test that one out first. Also, because it's more energy efficient.
Okay, again from the microphone on the left side.
First of all, thanks for your very nice presentation. I think I kind of imagined something completely different from, as for 3D printing. But this microwave vehicle that you showed that basically creates streets, right? Or paths. If you want to make a structure out of it, how do you raise it up? Like, how do you build something with it?
So let me go back with that. So the basic idea from that ESA is proposing is that you actually have some glue thingies. So they are applying glue at certain parts or binding material, to be more precise, and then they're using bulldozer kinds of things to put on the next layer. And with microwave, you could actually do the same. So you can build one layer, then you put on the next material on top, and then you go over it again. The problems with that is that we don't have enough samples to know anything about the material that is deep within the regulus. So we know that the microwave-based thing has been tested with Apollo 17 dust, about 80 grams of it. That was collected from the surface. The problem is we don't know whether the same properties are applying at material at a bigger depth. So there is a lot of research that could be done on the moon to know about that. But that would be the basic way of building something, that you use a bulldozer, put up material, you microwave it, you put the next layer on. This is not for printing a gearbox or something. This is for building structures like these.
Okay, next question, the right microphone in the front.
Yeah, I think my question is more for you specialists in front, but how do you intend to make those microwaves on the moon? You use magnetrons, or it's not something that is light or and you need a lot of power. So
actually, this is the funny thing about the magnetron. It's the energy that you need for getting the material up to 1,200 degrees is actually just 200 watts, and you just need it for what was it? I think it was 30 seconds, because you have the thermal runaway reaction going on when with the microwave. So you don't need much energy. So that's one of the significant advantages over laser. And about the weight and the size of the magnetrons, well, yeah, that's
and the heating.
Pardon?
You have excess heating.
For the what?
For the magnetron.
Yeah.
Because you're gonna dissipate. There is no atmosphere, so.
Yeah, I mean,
radiator or something.
Yeah, getting rid of heat is always very difficult because you don't have an atmosphere, so you need to dissipate it by infrared radiation. But this is, for example, something that we are doing in our rover as well. If we need to get rid of the heat, and the basic way you are doing that is that, for example, with a solar panel, we are building a shadowed area, and we have the one side of the tunnel where the electronics are sitting in the rover is pointing at the black stars, the black space, and so you have here you have then a lot of cooling that is going on, and radiative cooling can be very efficient, especially when you're using special coatings. So I didn't know that, but it's really cool. There's a color that you can put on something, and it only has a 10% solar acceptance, so you just get 10% from the solar heat inward, but you can still radiate 90% of the energy that it's heating, that's emitting. So that's pretty cool.
Okay, the next two questions from the internet.
Yeah, they're completely unrelated. Start with the first one. Since the regular simulants are not really adequate, do you know of any robot missions that are planned to bring some of the stuff back?
If I remember correctly, the Chinese mission, the last one, was actually there was a flyby, and they were testing the whole bring material back mechanism. And it was the next mission, which should be Chang'e 3 or 4. They actually want to bring material back. So that will be the first time in a few decades that new material from the moon is coming back.
And the completely unrelated question, what are the requirements to join the PT scientists?
So, actually, the requirement is that you're interested in doing something crazy, and that you're passionate about what you're doing, that you want to contribute. You know, you can contribute as in part-time, so you don't have to quit your job and start with us. If you want to be working for us full-time, it gets a bit more challenging. But we're always accepting new applications, and so if you're interested in helping us, doing anything with us, just send me an email with what you're interested in doing, and we'll find something. There should be a form on the website, which usually does not work, where you can apply officially.
Okay, we still have a few questions. The left-hand side rear microphone, please.
Hi. What layer size are we looking at with the microwaving? Like maybe with the rover, or how thick can you microwave? Like microns, millimeters? Like
No, actually, it's quite thick, so it's about centimeters. If I remember correctly, there is in the paper that they were talking about 3 to 5 centimeters, but I would have to look it up. There was a very nice paper from someone called Taylor, who's really into geological things, and it's very worth reading about it. It's also cited in the slides. Let me find that one. Yeah, here. So it's the microwave sintering of lunar soil by Taylor. If you Google Taylor and lunar thing, there are multiple Taylors, but they're all doing 3D printing on the moon, which I find very interesting. I think that the depth was rather surprisingly big.
And are you going to do it with your rover, or is it just?
No, so we are not going to do it with a rover, okay. Or very most likely not. The idea would be on our rovers we have something that's called drop container, which are triangular structures that are sitting below the solar panel, and they can actually fall on the surface of the moon. And then they deploy, and then you have like some solar power on the sides, and you have some experiments in the middle. And the idea is to use one of those drop containers for putting the microwave experiment in there. So it would drop on the surface somewhere outside our landing area.
Thank you.
Okay, the next question from the right-hand side microphone.
Hello. So you mentioned this stepwise procedure where you do something less ambitious, like your first goal is to land the rover. Have you considered applying that to the 3D printing too, and perhaps starting out with something like what was mentioned by ESA, like bringing a binding agent and trying to see if that'll produce usable 3D prints first?
Well, yeah, that's. I mean, that would be a fair idea. But on the other hand, microwaves. So the microwaves are, I'm a computer scientist, and I like microwaves. I don't like chemicals. So yeah, it's. I think that that doing the microwave thing is easier than probably the binding material thing. And also from a scientific perspective, it adds more value because you know that with a binding material you can create structures, and with a laser you can build things as well. But with the microwaving thing does not work with the simulants, which is I think makes it even more interesting to actually try it on the surface on the first try.
Okay, another question from that microphone, please.
How do you plan to look at the decomposing rover of Apollo 17? Do you just want to take a picture, or will the rover have some special device?
Yeah. So the thing is, our rover, as you saw. Oh, okay. So the question was how we are actually going to analyze the rover material, and the thing is that, as you can see in a rover, we have 3 cameras, and 2 of which are color sensors, which are wide angle, so those are used for driving, and the middle one is a telelens with a black and white sensor, and in front of the sensor there is a color filter, so that you can look at different wavelengths, and with that we can do some analysis about the material and how it is behaving. The problem actually would be to drive up to the rover and bump into it or something like this, because there is some guidelines on how to approach the Apollo landing sites, and there are some protection areas where we are not allowed to land, and there are the protective areas where we are not allowed to drive in. And fortunately, at Apollo 17, the lunar rover that they use for driving is actually standing outside of the protection area for driving by. I don't know if that is intentional or a mishap. So we would not be violating it by bumping into it, but we are not trying to.
Okay, I'm looking at the Signal Angel. Does the internet have any questions? The internet is very happy about the questions that are being asked right here. So the rear left microphone there, please. The next question.
Beside lasers and microwaves, have you the moon have a really good vacuum, like a old school cathode ray tube, and have we the possibility to use electron beam cannon on the regolith?
I mean, in theory, you can use any heat source that is able to get the temperature of the regolith to a certain degree of Celsius. So maybe I don't know if anyone tried. So I don't know. Sorry.
Okay, the next question from the right-hand side front microphone.
Have you thought of printing parts of the rover at the moon? Because then you wouldn't have to send up so much mass, and for example, you could send up a rover with little gears, so you can drive to a better place for printing bigger gears.
I know what you mean. Yeah.
Yes.
Have you actually used a 3D printer?
Yes, I have.
So the problem is, in theory. So I was at a presentation, and that was very funny. There was some guy who said, "Okay, my next startup is about solving a problem with the 3D printing industry, and that is that the data files that you are transmitting to the printer are not encrypted." And so I will ensure that Airbus can send the 3D printing files to a 3D printer on an airport, and so they can replace a part on an airplane just in time. If you use a 3D printer, you know that is very far from how everything goes. It's even with. I mean, if you look at the at our aluminum wheel that you can see here, you still have those rings, and they are coming from the fact that the material is contracting while you're printing it. And while this is a very known problem when you're using, how do you call Gießen? When you're using casting techniques, and the software can compensate for that. But in 3D printing, this is still unknown. And you know, it would be nice to print something useful, but I think we are far from that. So baby steps first, land on the moon softly, collect the money, and print something.
Okay, very good. We have a question on the left-hand side front microphone.
Yeah, I'm sorry, I'm still kind of stuck with the building structure thing, and I probably know that you can't answer all these questions, and there are still answers to find. But if you have the rover that runs over the surface and then beams microwaves at the ground, and then later have the bulldozer to put new soil, dust, whatever, onto the microwave platform, and then again have the rover go onto it again. If you go up, like, I don't know, 2 meters high or so, at some point your rover will have problems climbing that wall, wouldn't it? And and so my question is, how far away from the soil do you have to be to microwave it? Like, can't you build a satellite that, I don't know, beams it down?
So, the energy is lost by the radius square. So, if you want to deposit, if you want to deposit 50 watts into the lunar surface, and you are 3,000 kilometers away, which is like a good orbit for a lunar satellite, just do the math. You know, that's a lot. You would need a really big satellite, and then I would probably use laser, because lasers are cool. And but the basic idea about the first question is actually, you define the slopes to be in such a way that you can actually drive them up. And you also see that they are using those, how do you call them, the caterpillar thingies. Well, that's a bad idea. So this is an artist rendering. You know, it's a good idea, but the practical problems still lay ahead a lot. There will be a lot of PhD theses about this stuff.
Okay, we actually still have time for Q&A. So there are questions from the internet. Second Andrew.
Yeah, there's one more question from the internet, and they're still not quite over that regolith simulants thing. So the question is, why are the regolith simulants so bad?
Let me find that slide. So, the thing that when you have iron on earth-bound things, it's usually an oxide, and those oxides don't react as well to the microwave as an elemental unoxidized iron. And the interesting thing about the lunar surface is that with the bombardment of the micrometeorites, there are those glass beads which are actually forming, and with the radiation, some iron oxides actually degenerate into this elemental iron. And usually regular simulants are done by the ingredients. So you look at the regoliths that you collected on the moon, and you take in all the materials, so that when you're doing a when you're analyzing the ingredients, you get the same bill of materials, to say, and then you look at the grain size and you make it fit like this, and that's about the state of current lunar regolith simulants. They are not exposed to the radiation from the sun that you have. They are not They are not in vacuum. They usually don't have those glass beads forming. They are not shot at with micrometeorites. So in this way, you have the most regoliths don't actually have those nanophosphate, nanophase iron in them. That's the whole point of it.
Okay, so there's another question on the left-hand side rear microphone, please. Yeah, that's you.
Have you ever investigated and researched the idea of making something like bricks by just compacting the lunar dust or something like that?
Yes, there have been tests with some of the material, but it was found that it's because of the shape of the material. It's very coarse. It has very rough edges, and because of that, it's not very well compressible. To say it like this, I don't know if that actually makes it a good building material for something like this or not. Yeah. So the answer is I don't know, because no, we didn't try. But I would say that the density, you can't compress it enough. You will always have some air or some vacuum trapped in it, and it might be difficult.
Mm-hmm. Okay.
Okay, same microphone, please.
Have you looked at the Solar Sinter project?
The what?
The Solar Sinter project.
That was the guy with the big ass. Thing
about
in
1
the
square
desert?
meter, I think.
Yeah, exactly. Yeah, so that's really cool. But as I said earlier in the question is that the problem with bringing a big badass lens to the moon is bringing it there, and also the weight. This weighs a lot, and then you still need to have the mechanicals to move it and to do something with it. So it's a really cool project. I like that, but it's very difficult to do on the moon.
Okay.
Okay, so on the right-hand side front microphone, please.
It's just a follow-up to that bricks idea. Maybe we could put some lunar dust together, then microwave it into the brick, and then use a robot to put the bricks together, and then microwave them together.
Yeah, that would be cool. Yeah, baby steps first.
Okay, a question from the internet, please.
Yeah, there's one more question from the internet. Why don't you just dig caves to build houses, or build a cube with microwaved regolith and dig a hole in it or mill it?
Sorry, what? What was the first part?
The first part was, why don't you just dig a cave and build houses?
Oh yeah. So you don't actually have to dig a cave. There are already caves that you can use and that are ready to move in. So this is, but you still have to put in something there, but like interior design. But this is one of the ideas that is actually actively talked about. So the cool thing about the lunar surface is that you actually have something that's called lava tubes. And some of those lava tubes have openings where you can actually drive into. And I think this is a very interesting idea to build a settlement by becoming lunar cavemen again. But this is not us. So also ESA wants to do 3D printing, and whoever pays us, we will deliver.
And the second part of the question was build a cube with microwaved regolith and dig a hole in it or mill in it.
Yeah. Sure. Yeah. So there are many ideas that are ranging from something we should do in our first mission and something that maybe someone should do. I would put it here.
Okay, I see the microphones are empty right now. The internet is apparently satisfied also. That's a great thing. That was a great talk and a great Q&A session, especially. So thank you.